The potential costs due to equipment damage, interruption of power, and associated safety issues give a high priority to protection. For example, if a small section of aging insulation in a large distribution transformer fails, high levels of fault current will flow. If the fault isn't isolated quickly, the fault current will cause the conductors to heat. As the temperature of the conductor rises, the damage will spread to the surrounding insulation, causing it to fail, and the fault current will increase even further. As the level of fault current increases, the temperature will rise to a level that will melt the conductors and burn the steel laminations, resulting in catastrophic damage to this inadequately protected transformer. There are many causes of power system faults: lightning, wind, ice and snow, storms, flying objects, insulator contamination, physical contact by animals, human errors, falling trees, and aging insulation, to mention a few. The protective system must be able to sense faults and take appropriate action within a time frame necessary to minimize damage. Faults may be intermittent or permanent in nature. Lightning striking a transmission line or strong winds causing two phases of a transmission line to touch are two examples of an intermittent fault. The resulting arc ionizes the air and turns it into a conductor. The arc is then maintained by the power in the line. In both cases, the protection system responds by removing power from the line for a period of time long enough to allow the ionized air to dissipate. Power is then reapplied to restore service. Physical damage to a power system component, such as the transmission line or towers, are two examples of permanent faults. The protection system must be able to quickly sense and isolate the faulty components to minimize damage. In the following sections, we will show you how to set up the universal relay to meter currents and voltages from a power system, and then set up protection elements to properly clear any faults that occur. We will then show you how to use the universal relay and the URPC software to analyze any faults that occurred, so that appropriate action can be taken to reset the power system devices. In the universal relay, all current and voltage inputs are connected to the DSP module. The DSP module has 8 rows of inputs on its terminal block. Each row of inputs is used for measuring one phase of current or voltage. These DSP inputs are always grouped into 2 sets of 4 rows. Each group is used for measuring the currents or voltages from one power system circuit. The first row in a DSP group measures phase A. The second row measures phase B. And the third row measures phase C. When the group is used to meter current, the fourth row measures the ground current. When the group is used to measure voltage, the fourth input is used for measuring an auxiliary voltage that can be used for synchro checking. The UR allows up to 3 DSPs to be installed in one relay, each with 2 groups of inputs. In order to distinguish between the many groups of current and voltage inputs that can be found in one UR, a 2-digit naming convention has been given to each group of inputs. The name for each group of inputs is identified first by the slot location of the DSP, followed by the location of phase A for that particular group of currents or voltage inputs. If one set of currents is connected to the first group of inputs on the DSP located in the F slot, phase A would be located on row 1 of that terminal block. Therefore, that particular group of current inputs would be named F1. If a circuit is connected to the second set of inputs on the DSP in the F slot, phase A will be located in row 5. Therefore, the name given to that particular group would be F5. All DSPs installed will follow this naming convention. We now need to explain the concept of sources. Sources are used to connect one or more groups of DSP inputs to protection elements. The DSP input groups are assigned to a source, which is then assigned to the protection elements. Each DSP installed in the UR provides 2 sources for configuring. Configuring of sources must be performed before the UR will meter voltages and currents. To configure the UR sources, open the Sources Settings window, which can be found under Settings, System Setup, Signal Sources. URPC will display 2 sources for each DSP installed in your relay. In the Source 1 column, open the pull-down menu labeled Phase CT. In this window, you will see a listing of all of the groups of current inputs that are available on your relay for you to select. As you can see, you also have the option to select the sum of 2 or more DSP input groups. From the selections listed, choose Current Source F1 to be used as the input for Source 1. The Ground CT field allows you to select the ground current inputs to use in Source 1. Normally, this will be from the same DSP input group as your phase CTs. In this example, we will select F1. In the Phase VT field, enter the group of voltage inputs to use in Source 1. For our example, we only have one group of voltage inputs, so we will select F5. The aux VT input is normally used for the synchro check feature. Save these settings to the relay by pressing the Save button. We now have assigned the current and voltage DSP inputs to a particular source. This is the first step needed in configuring the relay to correctly meter currents and voltages being injected into it. For the UR to properly protect power system devices, some specific information is required. These settings can be found in the Settings, System Setup, Power System Settings window. The nominal frequency field needs to be set to match the frequency of your power system. The default setting is 60 Hz. If your power system differs from this, you will need to change this setting to match your system frequency. Now, configure the phase rotation field by opening the pull-down menu and selecting either ABC or ACB rotation to match your power system connections. The frequency and phase reference setting is used to simplify the viewing of vector diagrams by providing a point of reference to compare all other vectors against. For our example, we will leave the setting to the default of Source 1. Now, all other vectors will be compared to the Source 1 vectors. The frequency tracking function should only be disabled in very unusual circumstances. Consult the factory for special variable frequency applications. Write these settings to your relay by pressing the Save button. Once the UR has had its sources configured, it will be able to measure the magnitude of the voltages and currents that are being injected into the back of the DSP. This is known as metering. To view the UR's metering values, expand the Actual Values, Metering, Source menu. Here you will see a listing of all of the different types of measurements that the UR makes. In older versions of firmware, these measurements may all be listed under one group called Source Values. To view the currents being injected into the relay, click on the Phase Current menu item. The pop-up window will display one column of current values for each source that is configured. In each column, you can see the RMS value for phase A, B, and C currents of that source, as well as the neutral RMS current, which is the vectoral sum of phase A, B, and C currents. Further down in the column, you can see the phasor values for phase A, B, C, and neutral currents, which show the magnitude and angles of the currents measured only at the fundamental power system frequency. Also shown in this column are the zero sequence, positive sequence, and negative sequence current magnitude and angles. To view the voltages being injected into the relay, click on the Phase Voltage menu item. Just like in the Current pop-up window, the Voltage pop-up window will display one column of voltage values for each source that is configured. Each column will show the RMS and phasor values for the phases to ground voltages, as well as the RMS and phasor values for all of the phase-to-phase voltages. Also shown in this column are the zero sequence, positive sequence, and negative sequence voltage magnitude and angles. Since the magnitude of currents and voltages from the power system are much too high to be injected directly into the UR, these inputs are scaled down through current transformers, CTs, and voltage transformers, VTs. In our example, we are using a 100:5 ratio CT. This means that when 100 amps are passed through the CT, 5 amps will be injected into the relay. The VTs that we are using have a 1200 to 120 volt ratio, which means when 1200 volts is seen on the line, 120 volts will be applied to the relay. You need to configure the UR to match the amount that the CTs and VTs are scaling down these inputs. To scale the current inputs, you need to set the current CT ratio. To configure the current CT ratio for each set of current inputs, open the Settings, System Setup, AC Inputs, Current menu window. In this window, you will see that there is a column of settings for each group of current inputs that is installed in your relay. In the first two fields, we will be entering the primary and secondary values of RCT. In the phase CT primary field, type in 100 amps. In the phase CT secondary field, select 5 amps from the pull-down menu to match the secondary. In the ground CT primary and ground CT secondary fields, enter the primary and secondary ratio values of the ground CT you are using. To configure the voltage ratio for each set of voltage inputs, open the Voltage menu window. In the phase VT connection field, select either Y or Delta from the pull-down menu to match your wiring configuration. The phase VT secondary field represents the voltage being applied to the relay under normal conditions. To obtain the value needed to be entered here, you first need to determine whether your VTs are connected in Delta or in Y. If your VTs are connected in Delta, take your nominal primary voltage and divide this by the VT primary value. Now multiply this answer by the VT secondary value. This is the number to enter in the phase VT secondary field. If your VTs are connected in Y, as they are in our example, take your nominal primary voltage and divide this by the VT primary value. Now multiply this answer by the VT secondary value divided by the square root of 3. Enter this number in the phase VT secondary field. In the phase VT ratio field, enter the ratio of the voltage transformer being used. In our example, the voltage transformer being used has a 1200 to 120 voltage ratio. Therefore, the value entered in the phase VT ratio should be 10 to 1. The auxiliary VT settings are only needed when using the synchro-check function. These settings can be left at the defaults for now. If we now take a look at the actual values for current and voltage, you will notice that the values have now been scaled by the ratios that you have entered. The universal relay contains functions known as elements that constantly monitor electrical signals from the outside world and compares them with a set quantity. If the magnitude of that signal exceeds the set quantity, the element will notify the UR to take appropriate action. This notification is done through the setting of output flags. Each element has 3 different output flags that it controls. These are the pickup flag, the operate flag, and the dropout flag. We will use a simple overcurrent element example to describe how these flags operate. An overcurrent element is used to detect when the current has risen above a level that can be deemed dangerous. For this element, we will use current as the input. The value that we are comparing the current against, which is known as the pickup level, will be set to 100 amps. Initially, the level of current being input to the element will be 0 amps. At this time, the pickup flag and the operate flag will be off, and the dropout flag will be on, because the current is not above the pickup level. We will now increase the level of the current being input to the element. As soon as the current rises above the pickup level, the pickup flag will turn on and the dropout flag will turn off. Notice that the operate flag turned on at the same time as the pickup flag because this element had no programmed time delay. Normally, the operate flag turning on is the signal that the UR would use as notification to take action, such as tripping a breaker. As the current drops below the pickup level, the pickup and the operate flags will turn off, and the dropout flag will turn on. We will now add a 3-second pickup delay and a 2-second dropout delay to the overcurrent element. These timers will delay the changing of state for the operate flag. Now as the current rises above the pickup level, the pickup flag will immediately turn on, and the dropout flag will turn off. The pickup delay timer will now begin counting. Once the timer reaches 3 seconds, the operate flag will turn on. As the current drops below the pickup level, the pickup flag will turn off, and the dropout flag will turn on. Now the dropout delay timer will begin counting. Once the timer reaches 2 seconds, the operate flag will turn off. In the UR relay, there are several common settings that must be programmed in most elements. These settings are the function setting, the source setting, the pickup setting, and the block setting. We will use the instantaneous overcurrent element to explain these settings. The settings for the IOC can be found under Settings, Grouped Elements, Group 1, Phase Current, Phase IOC. The first of the common settings that we will discuss is the function setting. The two choices available for this setting are Enabled and Disabled. When the setting is programmed as Enabled, the UR will evaluate this element every protection pass, which is every 2 milliseconds. If the setting is programmed as Disabled, this element will perform no function in the relay. The source field allows you to select which source will be used as the input of the element. Since the UR can be used to protect multiple circuits, using multiple sources of current and voltage, each element needs to be programmed to know which inputs to monitor. The pickup setting is used to compare the input of the element to a certain value. The pickup level is usually set in per unit quantities. The block function is used to dynamically block the operation of any element. The input used for blocking the element can be any digital state in the UR, such as a contact input or the state of any other protection element. Blocking an element has the same effect as disabling it. Most protection elements operate on a per-phase basis. Therefore, the UR gives you the ability to block the operation of these elements on a per-phase basis as well. Some settings for current and voltage elements are specified in per unit calculated quantities. The per unit value is based on the CT or VT ratio that you configured for that particular source. If the selected element is monitoring current and the current input has a CT ratio of 100 to 5, 1 per unit would be 100 amps primary. If a pickup setting for this source of current needed to be 50 amps, the setting entered would then be 0.5 per unit. If the selected element is monitoring voltage, and the voltage input has a nominal secondary voltage of 120 volts and a VT ratio of 10 to 1, 1 per unit would be 1200 volts primary. If a pickup setting for this source of voltage needed to be 2400 volts, the setting entered would then be 2 per unit. The UR contains many elements that perform many different actions. These elements fall under two categories: grouped elements and control elements. The defining characteristic of a grouped element is that the element's configuration, such as the pickup settings, are subject to change based on the state of the power system. An example of a grouped element is the timed overcurrent element. Control elements normally have a control or protection function, where the configuration of the element is never likely to change. Examples of these control elements are the auto-reclose and the under-frequency elements. It is often beneficial to have the flexibility of having different protection pickup levels for different power system conditions. For example, in the winter, the demand for power is much lower. Therefore, the pickup levels for overcurrent can be set to lower levels. In the summer months, the demand for power is much greater due to the high use of cooling equipment, such as air conditioners. Therefore, the pickup levels for overcurrent need to be set much higher at this time. The universal relay contains 6 different groups of settings where you can configure the characteristics of each protection element. You can then switch between the different groups, thus changing the way you protect power system devices. The method of selecting which setting group is active can be found under the Settings, Control Elements, Setting Groups menu. In the menu window, you will see a field labeled Function. If this setting is set to Disabled, the UR will only allow the elements that are programmed in Setting Group 1 to be active. If the function field is set to Enabled and the Save button is pressed, you will then have the ability to select which setting group will be active. When the function field is enabled, by default, Setting Group 1 will be active. You can see this by looking at the field labeled Current Setting Group at the bottom of the window. To select Setting Group 2 to be the active setting group, you need to select a UR digital operand that will turn this group on. In the Group 2 Activate On field, select Virtual Input 1 On and press the Save button. Open the Command Virtual Inputs menu found under Commands, Virtual Inputs. Turn on Virtual Input 1 by selecting On from the State field and pressing the Save button. Notice that the current setting group field has now changed to 2. Now the protection elements that are configured in setting group 2 are active, and the elements in group number 1 are inactive. If more than one setting group has been turned on in the setting group menu at a time, the highest numbered setting group that has been turned on will be active. To demonstrate this, we will turn on setting group 5. In the Group 5 Activate On field, select On from the pull-down menu and press the Save button. Notice that in the current setting group field, setting group number 5 is now shown to be active because it is the highest numbered setting group that has been turned on. We will now again make group number 1 the default group by disabling this feature. The settings for most protection elements can be found under Settings, Grouped Elements. In the Grouped Elements menu tree, you will see 6 setting groups. Each setting group contains the exact same settings for each protection element available in your relay. Expand the Group 1 menu tree. Here you will see the submenus for different types of protection elements available in your relay. These lists will be different for each model of the UR, since the different models use different types of protection elements to protect their power system devices. The protection menus that will be available in most UR relays are phase current, neutral current, ground current, and voltage elements. Further expand one of these protection menus by clicking on phase current. Here you will see a listing for the timed overcurrent, instantaneous overcurrent, and the phase directional elements. To access these settings, you can double-click on the menu item, and the settings for that protection element will appear in the workspace. Expand the Group 2 menu tree. You will see that the categories listed here are exactly the same as the ones listed in Group 1. Further expand the phase current menu, and you will also see the same protection elements that are listed in Group number 1. The settings for each protection element can be configured in all of the settings groups, but only the setting group that has been enabled by the group control element will have any function in the relay. All other setting groups will be idle until that group has been selected to be the active group. The instantaneous overcurrent, or IOC element, is used to prevent damage from occurring to individuals or to the power system by detecting when the magnitude of current flowing through the power lines is above the level that has been deemed to be dangerous. This is known as a fault. When an IOC element detects a fault, it will immediately eliminate this condition by signaling a breaker to open the path of current flow. The IOC element must first be configured before it can be used to detect an overcurrent condition. Open the IOC Settings menu found under Settings, Grouped Elements, Group 1, Phase Current, and Phase IOC. In this window, you will see 2 IOC elements for each set of current inputs you have in the DSPs installed in your relay. In our case, we only have one DSP installed that has one set of current inputs. Therefore, we will have 2 IOC elements in this group. The first setting that must be configured for this element is the function setting. The default setting for this field is always disabled. This setting must be changed to enabled before this element will have any function in the relay. Next, we need to configure the source setting. The source setting selects the set of current inputs that the IOC element will use to detect a fault condition. Our relay has one set of current inputs that was previously configured as source 1 in the signal source movie. Therefore, we will select source 1 for this setting. The pickup setting specifies the minimum magnitude of current that the IOC element will identify as a fault. Once the current rises above this level, the IOC element will operate and notify the UR to take action. Notice that this setting is specified in per unit quantities. Since we previously set our current CT ratio to be 100 to 5, 1 per units is equal to 100 amps. If we want our instantaneous overcurrent element to identify a fault at, say, 600 amps, we would set our pickup setting to 6.0. The following 2 settings are delays that can be added to the operation of the IOC element. The delay setting adds a fixed time delay between the picking up and the operating of the IOC element. We will set this delay to 3 seconds. Let's look at an example of this so you can fully understand the delay function. The table shown here will illustrate how the UR's IOC will operate over time with respect to varying current levels. This graph will plot the current magnitude on the y-axis against time on the x-axis. The dotted line represents the pickup level, where any current value above that magnitude is identified as a fault. Under normal conditions, the current will be well below the pickup level. At the time of a fault, the current will rise above the pickup level. Now the IOC element will pick up and set an internal flag indicating that it has picked up, and the delay timer will start counting. Once the current magnitude has been above the pickup level for a time period that is greater than the delay setting, the IOC element will operate and set an internal flag to indicate this. The reset delay adds a fixed time delay between the dropping out of the element and when the operate flag turns off. We will set this delay to 2 seconds. As shown in the example here, the IOC pickup and operate flags are currently in the on state. When the current drops below the pickup level, the IOC pickup flag will immediately turn off and the dropout flag will turn on. Notice that the operate flag is still on. After the magnitude of current has been below the pickup level for a time period greater than the reset delay, the operate flag will turn off. If you do not want to add any intentional delays to the operation of the IOC element, leave both the delay and reset delay settings to 0. The blocked settings can be used to block the operation of this instantaneous overcurrent element. This can be useful in situations where you want to block this UR from tripping because a downstream relay also detects the fault and has the ability to clear it. If you open the pull-down menu, you can see that you have the ability to block the IOC element with any digital operand in the UR, including contact inputs, virtual inputs, as well as the status of any other protection element. As you can see, you also have the ability to block the operation of the IOC element on a per-phase basis. Simply select the UR operand that will block that particular phase. If you wish to have the instantaneous overcurrent element blocked by the same operand for all 3 phases, simply select that operand in each of the 3 fields. The target field controls the messages that will be displayed on the front panel at the time of an IOC element operation. If the target field is programmed to be self-resetting, the message IOC operate will appear on the front panel display when there is an overcurrent fault condition. Once the fault condition has been cleared, the message will disappear. If the target field has been programmed as latched, the message IOC operate will appear on the front panel when there is an overcurrent fault condition, but will stay there even after the fault has been cleared. The only way to remove the IOC operate message is to press the reset button on the front panel or by sending a reset command from a manual control station. If the target field is programmed as disabled, no messages will be displayed at the time of an overcurrent fault. The event field lets the UR know if it should record the operating of the IOC element in the event record. Select Enabled if you want these events to appear in the event record, and Disabled if you do not. Be sure to press the Save button to save these settings to the relay. We will now test the instantaneous overcurrent element that was previously configured in the IOC movie. To open this setting window, click on Settings, Grouped Elements, Group 1, Phase Current, and Phase IOC. Here you will see the pickup level has been set to 6 per units, which corresponds to 600 amps primary. There are no intentional pickup or reset delays added. The target field has been set to latched, and the events field has been set to enabled. It is very important that the events field be set as enabled so that we will be able to perform troubleshooting of the fault when looking at the event record later in this movie. The power system is currently in the non-faulted state, and the magnitude of current is below the pickup level. Once a fault occurs, the current flowing through the power lines will increase above the pickup level. Several things will now occur in the UR. First, the instantaneous overcurrent element will have its internal pickup flag turn on. Because there is no intentional delay added, the operate flag will turn on at the same time. Since the target field was programmed to be latched, the UR will also indicate on the front panel that there is a fault in the following manner. The pickup LED will turn on, indicating that at this very instant there is an active fault condition. The current LED will turn on, indicating that the type of fault present is current-based. The phase A, B, and C LEDs will turn on, indicating the fault condition is found on all three phases. If the fault were only detected in one phase, the UR would only have turned on the LED for that corresponding phase. The front panel display screen will also display a message, Phase IOC Operate, Phase A, B, and C. This indicates which protection element operated and which phases the fault was on. All of these events and messages will occur simultaneously, immediately after the UR has detected an overcurrent condition. Remember, at this point, the instantaneous overcurrent element is only setting a flag inside the relay when it detects an overcurrent condition. Before the UR can change the state of a contact output to signal the breaker to trip, the IOC Operate flag must first be assigned to that contact output. The method of assigning a contact output to operate is covered in the FlexLogic primary control section of this learning CD. Once the associated breaker has tripped and cleared the fault, the current will drop below the pickup level. When this occurs, the IOC pickup and IOC Operate flags will turn off, and the IOC dropout flag will turn on. On the UR front panel, the fault indicators will be affected in the following manner. The pickup LED will turn off, indicating that the fault condition is no longer present. The current LED and the phase A, B, and C LEDs will stay on because the target field was set to latched. The message displayed on the front panel display screen will change to Phase IOC Latched. Both of these indicators will stay on the front panel so that the cause of the fault can be diagnosed very quickly by sight. In order to make these messages disappear, the reset button needs to be pressed or a reset command needs to be sent from the manual control center. Since the events field for this protection element was set to enabled, we can obtain more details on this fault by looking at the event record. To open the event record, in the online window select Actual Values, Records, Event Record. This event record will show a time-stamped sequence of what occurred at the time of the fault. At the bottom of the record, you will see a line showing the pickup of the phase IOC element for each phase. Activate the control of the blue cursor by clicking on the blue number 1 button at the top of the window. If you now click on the phase IOC1 pickup phase A line, the blue cursor will highlight this line. Activate the control of the green cursor by clicking on the green number 2 button at the top of the window. If you now click on the phase IOC1 pickup phase B line, the green cursor will now highlight this line. The yellow box at the top of the window will display the time difference between the two events that are highlighted by the cursors. Since the time difference is 0.0 seconds, you can see that all three of the phases picked up at the same time. Now move the green cursor to the line showing Phase IOC Operate Phase A. You can see in the yellow box that there was no time delay between the instantaneous overcurrent pickup and operate. Again, activate control of the blue cursor by clicking on the blue number 1 button, and then click on the line showing Phase IOC Dropout Phase A. In this case, it took 123 milliseconds to clear the fault and caused the instantaneous overcurrent element to drop out. Another method for gaining more information about the cause of a fault is through the use of the oscillography recorder in the UR. The UR must first be configured before it will record information about this instantaneous overcurrent fault. To configure the oscillography settings, open the Settings, Product Setup, Oscillography menu. The first field in this window determines the number of records that can be stored in the UR at one time. The UR has a finite amount of memory allocated for storing oscillography records. You can configure the UR to use all of this memory to record one long record, or split the memory up to record a larger number of smaller records. We will select 10 records for our example. The trigger mode will be set to automatic overwrite, which means that once all 10 records in the UR are full, any successive oscillography triggers will result in a new record being recorded and the oldest record being deleted. We will set the trigger position to be 25%. This will result in an oscillography where 25% of the record will show what happened before the trigger, and 75% of the record will show what happened after the trigger. The trigger source tells the UR when to start recording an oscillography. Since we want to record whenever the instantaneous overcurrent element detects a fault, we will set this field to phase IOC1 pickup. We chose the pickup flag to initiate recording an oscillography so that we will be sure to record all relevant fault data. If we had chosen the operate flag that had a time delay, we may have missed recording the point where the fault occurred. We will also leave the AC input waveforms field to record 16 samples per cycle. By default, the UR records the waveforms of each of the 8 inputs for each DSP installed in your relay. Any other digital or analog information you wish to record must first be programmed in the following fields. In Digital Channel 1, open the pull-down menu and select Phase IOC1 Pickup. In Digital Channel 2, select Phase IOC1 Operate. In Analog Channel 1, select Source 1 Phase A RMS Current. In Analog Channel 2, select Source 1 Phase B RMS Current. And in Analog Channel 3, select Source 1 Phase C RMS Current. Press the Save button to write these settings to the relay. We will again test the IOC element using the same settings as described in the IOC event record movie. The current being injected into the relay will transition from the non-faulted state to the fault state and cause the IOC element to pick up and operate. This will cause the UR to signal the breaker to trip and clear the fault. The IOC element will then drop out. Let's take a look at the oscillography file that was created for this fault. Open the menu, Actual Values, Records, Oscillography. In the window that appears, you will see information on the number of records available in the UR and which record is the newest record available. Also, you can see the length of the records that are being stored in the relay. For our oscillography configuration, each record is 209 cycles long, or about 3.3 seconds. To read the one record that was created when we had the IOC element pick up, press the Read button. The oscillography viewer will open showing the waveforms for the 8 input channels of the DSP and any other information that we configured the UR to record. To customize the information being displayed, press the Preferences button found on the top toolbar. In the Analog tab, you can configure which pieces of analog information to display in the viewer. For now, we will view only the Phase A currents to simplify the demonstration. In the Display Order column for F1 Phase A current, select Automatic. Remove the next 7 channels from being displayed in the viewer by selecting None in the Display Order field. Let's also choose to view the Phase A RMS current by selecting Automatic in the Display Order field for that line. In the Digital Channel tab, you can see all of the digital channels that we programmed, plus the trigger for the oscillography. Let's make sure we can view all of these channels by selecting Automatic in the Display Order field for each channel. Press the OK button. The viewer will now be modified to display only the information we configured. The top 2 channels will show the waveform and RMS values of Phase A current. The bottom 3 channels will show the status of the oscillography trigger, the IOC pickup flag, and the IOC operate flag. Move the blue cursor to the position where the IOC element picks up. Notice that the magnitude of RMS current is just above 600 amps or 6 per units at this point. Now move the green cursor to the position where the IOC element drops out. Notice that the magnitude of RMS current is just below 600 amps, or 6 per units at this point. If we take a look at the yellow delta field at the top of the window, We can measure the time between the two cursors and determine how long the current was above the pickup setting. In this case, you can see that the magnitude of current was above the pickup setting for 126 milliseconds before the fault was cleared. The time over current, or TOC element, is similar to the IOC element in that it is used to prevent damage from occurring to the power system. It does this by detecting when the magnitude of current flowing through the power lines is above the level that has been deemed to be dangerous. The difference between the two is that the TOC element uses an inverse time curve to vary the length of the delay between the pickup and operate of the element, depending on the magnitude of the fault current. For example, for the inverse time curve shown here, if we have a fault current level of 200 amps, the operate flag will turn on 1.3 seconds after the pickup flag. If we had another fault where the magnitude of the current was now 600 amps, the operate flag would turn on 0.2 seconds after the pickup flag. The TOC element must first be configured before it can be used to detect an overcurrent condition. Open the TOC Settings menu found under Settings, Grouped Elements, Group 1, Phase Current, Phase TOC. In this window, you will see two TOC elements for each set of current inputs you have in the DSPs installed in your relay. In our case, we only have one DSP installed that has one set of current inputs. Therefore, we will have two TOC elements in this group. The first setting that must be configured for this element is the function setting. The default setting for this field is always disabled. This setting must be changed to enabled before this element will have any function in the relay. Next, we need to configure the source setting. The source setting selects the set of current inputs that the IOC element will use to detect a fault condition. Our relay has one set of current inputs that was previously configured as source 1 in the signal source movie. Therefore, we will select source 1 for this setting. The pickup setting specifies the minimum magnitude of current that the TOC element will identify as a fault condition. Once the current rises above this level, the TOC element will pick up. Once the current has been above the pickup level for a time period longer than the time defined by the inverse time curve, the TOC element will operate. In the CT-VT ratio movie, we set our current CT ratio to 100:5. Therefore, 1 per unit is 100 amps. Let's configure our TOC element to pick up at 100 amps by setting the pickup to 1 per unit. The shape of the inverse time curve is determined by selecting one of the available industry standard curves, or creating one of your own through the flex curve function. For our example, we will select the IEEE moderately inverse standard curve. The time delay multiplier allows you to multiply the operate delay times by any number you wish. For example, if my normal inverse time curve would cause my TOC element to operate in 1.3 seconds at 200 amps of fault current, setting my time delay multiplier by 2 would now cause my TOC element to operate in 2.6 seconds. Likewise, I can set my time delay multiplier to 0.1, which would then cause my TOC element to operate in 0.13 seconds. We will set this field to 1.0 for our demonstration. Set the target to be latched, and the events field to enabled. Press the Save button. We will now test the timed overcurrent element. The power system is currently in the non-faulted state, with the magnitude of current being below the overcurrent pickup levels. At some point, a fault occurs, which is above the timed overcurrent pickup level. As soon as the magnitude of current rises above the TOC pickup level, the TOC pickup flag will turn on. At this point, the TOC element will begin timing how long the current has been above the pickup level. Once the current has been above the pickup level longer than the time allowed by the inverse time curve, the TOC element will operate and signal the breaker to trip. The accuracy of this time delay can easily be measured by checking the event record. Do this by clicking on Actual Values, Records, Event Record. Move one of the cursors on the line showing the TOC1 Phase A pickup, and the other cursor on the line showing the TOC1 Phase A operate. In the yellow box at the top of the window, we can see that the TOC operate occurred 1.3 seconds after the TOC pickup. Previously, we configured the oscillography to trigger whenever the IOC element picked up. Now, we want to trigger an oscillography when either the IOC element or the TOC element picks up. In order to do this, we need to create a flex logic equation so that either one of these two inputs will turn on a virtual output, and then assign that virtual output to trigger the oscillography. Let's open the Flex Logic Equation Editor by clicking on Settings, Flex Logic Equation Editor. We will start a new equation right below the last equation that was programmed. The first lines of this equation need to list all of the operands that will be able to trigger an oscillography record. We will list phase IOC1 pickup and phase TOC1 pickup. The next line of our equation will be an OR gate with two inputs to match the number of inputs listed previously. The last line of our equation will be the assigning of our equation to a virtual output. We will use virtual output number 64. Write these settings to the relay by pressing the Save button. We now need to configure the UR to record an oscillography whenever virtual output 64 turns on. Double-click on Settings, Product Setup, Oscillography. In the oscillography configuration window, change the setting in the trigger source field to virtual output 64. We now need to set which TOC element information we want to record in the oscillography. In the Digital Channel 3 field, select Phase TOC1 Pickup. In the Digital Channel 4 field, select Phase TOC1 Operate. Write these settings to the relay by pressing the Save button. We will again create a fault that will be picked up by the TOC element by injecting 5 per units of current or 500 amps primary. Notice the TOC element will pick up and then a short time later operate. Let's download the newly created oscillography record by opening the Actual Values, Records, Oscillography window, and then pressing the Read button. Here you can see the oscillography viewer is configured the same way as when we viewed the IOC operation record. But this time, the digital channels show the TOC element operating instead of the IOC element. The oscillography viewer by default only shows the digital channels that changed state during this record. Move the blue cursor to the position where the TOC element picked up. Notice at this point, the magnitude of current is just above 100 amps. Move the green cursor to the position where the TOC element operates. The magnitude of current at this point is roughly 500 amps. If we look at the yellow box to see the time difference between the two cursors, we can see that the TOC pickup and operate occurred about 1.3 seconds apart. This coincides with what was expected from the inverse time curve.